Welcome to this video. What we're going to be looking at today is centripetal acceleration and centripetal force. And so the first thing we're going to do is we're going to take a look at this circle I've got drawn here. Now this circle represents an object which is moving around with an constant angular velocity of omega. Okay, now that object's moving around in that circle, and its tangential velocity at different points will be represented by the two arrows VA and VB. Now if we were to work out the change in velocity between those 2 points, we'd have to add them as vectors, and it would become the change in velocity delta V is equal to your final velocity take away your initial velocity. So for us that'll be VB take away VA. Now because these are vectors, if we add them together using vector addition, we've got our triangle that I've set up here in advance. Okay, and so we've got VB and VA. And then this whole green line here would be delta V, the change in velocity. Okay. Now if we were to draw a line to bisect the hypotenuse there, we would be creating two smaller triangles. And we can work out the length of y using those smaller triangles. Okay. And so in that case, it would be that sine theta over 2 would be equal to y over v. Okay. Which means that if we rearrange that for y would be equal to v sine theta over 2. And so our total equation for delta v would be 2v sine theta over 2. Okay, now we're going to call that equation 1 because it's going to become really important. And what we're going to do now is we're going to think about our overall equations for velocity. Okay, and so velocity is equal to distance over time. Okay. We rearrange that for time is equal to distance over velocity. Now what we're going to do is we're going to say that the distance travelled by the object, okay, around that circle is going to be the arc length, right? So the distance travelled is going to be theta r, right? Because that's how we calculate our arc length around the circle, okay? And so, excuse me, and so substituting that in, t is going to be equal to theta r over v, okay? And what we're then going to look at is how this relates to acceleration. So acceleration is equal to the change in velocity over the change in time, okay? So if we substitute equation 1, and sorry I forgot to label this as equation 2, if we substitute those both in, we are going to get that acceleration is equal to 2v sine theta over 2 divided by theta r. Okay. Now, importantly, theta r over v. Sorry. Now, to get rid of the fraction on the bottom, we're going to multiply through by v, bring the v up, so it's going to become 2v squared sine theta over 2 all over theta r. Okay. From there, you need to remember that for small angles, sine theta is approximately equal to theta, and because we're dealing with radians, they're going to be small. Okay, and so let me just insert a new page here. And so our equation becomes the acceleration is equal to 2v squared theta over 2 divided by theta r. Okay. And so our going to cancel off terms. The theta will cancel there, the 2 will cancel with that one there, and we are left with acceleration is equal to v squared over r. Okay, and so that is one equation for the centripetal acceleration of an object going around in a circle. Okay, however, remember that V is equal to omega r, and if we substitute omega r in there, we will get AC is equal to omega squared r squared over r. That'll cancel off there with one of the r's on the top. And so another equation for the centripetal acceleration is omega squared r. And so that's how we derive our two equations for centripetal acceleration, okay? Now we're going to have a quick worked example to use this equation. So we have a disk of radius 0.5, okay, rotating with an angular velocity of 4.1 radians per second. What is the centripetal acceleration of a point on the circumference? Well, since it's given us omega is equal to 4.1 radians per second and radius of 0.5 meters, we can use AC is equal to omega squared r. So it's going to be 4.1 squared times 0.5, which is going to equal 8.4 meters per second squared. Okay? Nice and easy so far. From here, we're going to continue on looking at centripetal acceleration, and we're going to think about if something is accelerating centripetally, there must be a constant force acting on it, okay? And that's what we call the centripetal force. So, since the object's moving with a constant angular velocity, it'll have a constant centripetal acceleration, because we've got an equation that proves that the centripetal acceleration is equal to the radius times by the angular velocity. Which means that if we consider F equals ma, and we substitute in our centripetal acceleration as our A, our acceleration, then we can end up with two new equations. So F is equal to mr omega squared, or F is equal to mv squared over r. And this is the centripetal force, okay? So we have two equations to calculate the centripetal force of an object moving in a circle. Now this centripetal force is always going to be directed towards the center of the circle. So when you have something moving in a circle, the centripetal force will exist acting towards the center of that circle, okay? No matter what type of circle, whether it's horizontal, vertical, the centripetal force always acts towards the center of that circle, okay? And so when you're identifying the centripetal force, it could be that you're identifying the tension on the string that's holding the object in, or the centripetal force caused by the wall pushing on it, okay? But when you're dealing with centripetal force, it's the force acting towards the center, okay? Now, when you have an object moving in a horizontal circle, okay, the tension in this case becomes the centripetal force, the tension in that string, right? And in that case, we can deduce that if the tension of this string here is the centripetal force, then we can say that tension is equal to mr omega squared and mv squared over r. So the tension is equal to the centripetal force, right? We've got a worked example of this now. And so we've got a puck being spun in a horizontal circle with a radius of 0.5 meters. It is spinning with a constant angular velocity of 0.42 radians per second. What is the tension in the string? So writing down what we know to start with, we know that omega is 0.42 radians per second, and it has a radius 0.5 meters, and I forgot to give the puck a mass, so let's say it has a mass of 200 grams. Okay, so what happens when I write my own questions? I forget things. Okay, so we give it a mass of 200 grams, that's 0.2 kilograms. Now we can work out that the tension in that string is equal to m omega squared r. So that is going to be 0.2 times 0.42 squared times 0.5, which is going to come out as 0.018 newtons. Okay, So moving on from there, we're going to start looking at conical pendulums. Now, conical pendulums are quite exciting. I really enjoy these because the thinking required in solving these is quite complex. But it's really enjoyable when you get to the end of one of these, you feel like you've really achieved something. Okay? And so, if we consider we've got a conical pendulum here, okay? And the centripetal force is going to act along the radius, right? Because it always acts towards the center of the circle. The tension in this case is acting down the string. So those are not equal to each other anymore, because the pendulum is forming a cone, okay? We've got the mass, the weight, sorry, of the bob acting downwards, okay? So that's our mg, is the weight of the bob acting downwards. Excuse me. Now, what we're going to do is, if we analyse this circle, this triangle here that we've got set up, right? We'll be able to work out an equation to calculate the centripetal force, and also an equation to calculate the force acting upwards, okay, and the tension as well if we need to. So if we were working out FC, then we would be able to look at our trigonometry and say that sine theta, okay, is equal to FC over T. So if we rearrange that, we're going to get FC is equal to T sine theta. Right? Now, we know that the centripetal force is also equal to mv squared over r. Okay. Now, if we then look at cos, we're going to see that cos theta is equal to mg over t. Okay. And that's because the Fy and mg are going to be the same force due to Newton's third law. Now, from there, we rearrange that, we get mg is equal to t cos theta. Okay, that's equation 2, and we label this one equation 1 over here. Now, if we divide these two equations by each other, okay, then we would get t sine theta equals mv squared over r divided by t cos theta equals mg. As we start cancelling off things, our m's are going to cancel, okay, t's are going to cancel, and sine and cos, sine divided by cos gives you tan, something we're all getting in this weather. So tan of theta is therefore equal to v squared over gr. That just gives us a third equation that we can use. Okay, so these are our 3 useful equations for conical pendulums. Okay, now the other thing that's important to note is that the conical pendulum not only has the distances that the values you're calculating in terms of force and in terms of force and tension and stuff, but you also have the physical distances there. Okay, so we have a physical string with length L, and so we can work out the length of the radius or the length of the string depending on the same trigonometry using the physical values. Okay, so I'm going to give you an example of that just now. So we've got a big worked example here, probably going to take over 2 or 3 pages, so I might have to flip backwards and forwards to get this done. But worked example, a bob of mass 80 grams on the end of a string with length 1.2 meters forms an angle of 20 degrees with the vertical. Calculate the tangential velocity of the bob, the angular velocity of the bob, and the centripetal acceleration of the bob. Okay, so the bob is here, it's going round in a circle. Now, in order to work out any of those things, we need to first work out the radius of the circle. Okay, and so if we know that this L is 1.2 meters and we know that this is 20 degrees, then the radius, which we've got written on here along the FC line, would be r. Okay, then that radius would be the sine of 20 equal to r over 1.2 So R is equal to 1.2 times sine 20, which is 0.41 meters. And so that's our radius of the circle. Okay, and so that's how we would use the physical distances of this object to work out the radius of the circle that we can then use, because you can't do any of the other equations we worked out without the radius. Okay, so to work out the tangential velocity, now that you have the radius, what we're going to be doing is we're going to be using the two equations, 1 and 2, that we worked out, and dividing them to work out our tan equation. Okay, so we're going to end up with t sine 20 equals mv squared over r, because it's that v you're trying to work out. It's going to be divided by t cos 20 equals mg. Okay, and then those are going to cancel off, so the t's will cancel, again your m's will cancel, and so what you're going to get is that's going to be equal to tan of 20 is equal to v squared over gr. Okay, now if we rearrange that for v, you're going to get v is equal to the square root of tan 20 times 9.8 times r that you worked out is 0.41. Okay, and that gives us a velocity of 1.2 meters per second. And that's our tangential velocity of the bob going round in the circle. Okay, now for b, it becomes a lot simpler, but we'll need a new page. How do we relate our tangential velocity and angular velocity together? We have an equation that we learned where v is equal to omega r. So as we're trying to work out omega, omega is equal to v over r. So it's going to be 1.2 divided by 0.41, which is going to be 2.9 radians per second. That's our angular velocity. Okay, and then c, we have to work out centripetal acceleration of the bob. So AC is going to be equal to v squared over r. We know that v is 1.2 squared divided by 0.41, which is going to be equal to 3.5 meters per second squared. Okay, so it's quite a difficult example there, but hopefully it'll make a lot of sense for you. If you need to watch it again, give the video a rewind and give it another watch, okay? From there, we're then going to consider things in a vertical circle, okay? So we're going to be looking at the tension in the string of something that's rotating in a vertical circle. Like swinging a ball around beside your body or something like that. Vertical circles, okay? And so, at the top of this circle, okay, we've got tension acting down the way, and we've got weight acting down the way. And so what we've got is we've got those two acting down towards the ground. So if I define upwards as my positive direction, okay, just for keeping our sign convention correct, if I define upwards as positive, then our resultant force on the bob at the top is going to be equal to the tension at the top plus the weight acting downwards. That's going to add together to give our resultant force, okay? But since the ball is moving in a circle, that resultant force is going to be our centripetal force because it's keeping it in the circle. So that resultant of those two is the centripetal force acting towards the centre. So we could substitute in there that it's equal to m omega squared r is therefore equal to t top plus mg. And so if we rearrange that for working out the tension at the top is equal to m omega squared r take away mg. Okay, and then if we consider the vertical circle at the bottom, the tension is going to be acting towards the centre, but the weight is going to be acting in the opposite direction. And since the resultant force of these two has to be equal to the centripetal force, we're going to be having a bigger centripetal force at the bottom. Okay, so if we write this out, we're going to have the resultant force is going to be equal to T at the bottom, take away mg because they're acting in opposite directions. Okay, the mg is acting downwards and I'm saying tension upwards is going to be our positive. Okay, now we're going to start dealing with objects moving in a vertical circle. And so what we're going to do first is we're going to define our sign convention. So I'm going to say upwards is positive. And so if we look at the top of this circle, we're going to be looking at our resultant force, okay, which is going to be acting towards the center. Okay, that's going to be our FR, acting towards the center. So because it's acting downwards, it's going to be negative. So negative FR is going to be, both of these acting downwards as well. So it's going to be take away negative T top plus negative mg, okay, because you're going to add them together because they're both acting in the same direction. Now because they're all negative, I'm just going to change them all to positive because they're all just going to work like that. Okay, and now if we were trying to work out the tension at the, if we were going to look at the centripetal force here, this resultant force is the centripetal force because it's acting towards the center. And so we can say that mr omega squared is equal to T top plus mg. And so therefore our tension at the top is going to be equal to mr omega squared take away mg. Okay? And then at the bottom, our resultant force is acting towards the center, so FR is going to be positive, and that's going to be equal to T bottom plus minus mg, because mg is still acting downwards. So therefore FR is going to be equal to T bottom minus mg. And again, FR is our resultant, it's our centripetal force. So we substitute in mr omega squared is equal to the tension at the bottom, take away mg, excuse me. And if we rearrange this to work out the tension, T bottom is going to be equal to mr omega squared plus mg, okay? Showing that our tension at the bottom is going to be bigger than our tension at the top. Okay, so we're going to go for our worked example. And so what we're dealing with is we've got an object of mass 200 grams spun in a vertical circle with a speed of 5 meters per second at a radius of 50 centimeters. We have to calculate the tension in the line at the top and the bottom of the circle. Sorry. Okay, and so first thing we're going to do is we're going to define our direction for our sign convention. I'm going to say up is positive. And so at the top of the circle, we're going to do top first. Okay, we are going to have the tension acting downwards and mg acting downwards. And so our resultant force, which will be acting downwards with minus FR, is going to be equal to minus T plus minus mg. And so FR is going to be equal to T plus mg. Okay, now because it's being spun in a circle, we know that the resultant force is the centripetal force. So we can say that that's going to be equal to mv squared over r, because that's one of our equations for centripetal force. And so what we can do is we can rearrange this. And so tension is going to be equal to mv squared over r take away mg, which is going to be 0.2 times 5 squared divided by 0.5 take away 0.2 times 9.8. That's going to come out as 8 newtons at the top, okay? And then if we deal with the bottom, keeping our sign convention, okay, what we're going to be dealing with now is we've got the tension acting up the way and the weight acting down the way. And so our resultant force, which is going to be acting up the way, is equal to tension plus minus mg. And so our resultant force is equal to T minus mg. Our resultant force is the centripetal force, so mv squared over r is equal to T minus mg. So T will be equal to mv squared over r plus mg, because change side, change sign. We substitute in our numbers, 0.2 times 5 squared divided by 0.5 plus 0.2 times 9.8, and that's going to be equal to, it's 11.96 in the calculator because I'm round it to 12 newtons. Okay, that's us for this video. I know that's been a lot. You might need to watch it a couple of times to get it all to soak in. We're just looking at centripetal force and centripetal acceleration here. There are going to be some questions that you can do to practice this. I hope you've enjoyed the video. I hope it's been helpful. Remember to give the page a like and a subscribe so that you can see more videos like this when they